Hi and welcome to another episode from Spiral Physics Education. So in this lesson we're going to be looking at what causes resistance. We're going to be looking at current and resistance in series and parallel circuits, and then we're going to link all of that together to look at Ohm's Law and do a couple of examples of Ohm's Law questions. And what you need to know to make the most out of this lesson will be have an idea about what current is, also about voltage, and the rules for current in series and parallel circuits, along with rules for potential or voltage in series and parallel circuits as well. And if you're unsure about any of those, don't forget to check out other videos on the channel to help you get up to speed on those before you progress through this lesson. So let's start off with having a look at what causes resistance in a metal or a wire to start off with. So here we've got a wire, and these things in the wire are supposed to represent the positive ions that make up the lattice in a metal wire. And the thing to remember though is that current is the rate of flow of charge, and what resistance does, it reduces that rate of flow of charge. So if something has more resistance, then the current is going to be less because the charge is not able to flow as easily because of that extra resistance. So this animation now represents really a better animation of what's actually happening in a metal wire. Is that the positive ions are actually vibrating around fixed positions. So that's what's happening here, and what's going to happen when the current flows is that the charge tries to move about and around those ions, and you can see that if those ions were to vibrate more, then they get in the way more, and then there'd be more resistance, and that means that those ions, those blue blobs there, are not able to flow as easily. The charge would be restricted, or its flow would be restricted. So that's what we mean by resistance, is that the ions in a conductor vibrate around the fixed position and they restrict the flow of charge. So let's see what resistance does to current in a series circuit. So here we've got a series circuit with a resistor in, and that resistor allows a current of 0.5 amps to flow through it. So if we get a similar circuit but we add on another resistor, an identical resistor, what we've done here is we've doubled the resistance in that circuit. So if you think about it, if the resistance is doubled, then the rate of flow of charge, current, is going to be lower. In fact, it's going to be half the amount. So if we double the resistance, the current is halved. What about current in parallel circuits? So here we've got our original circuit where we've just got this single resistor in it, but we've added an identical resistor in parallel. So initially there was this 0.5 amps flowing. And because we've added another resistor, identical resistor in parallel, then 0.5 amps will also flow to that. And that means that the power supply is actually delivered 1 amp. It's delivered twice the amount of current compared to just one resistor. So in fact, adding a resistor in parallel like this actually causes the current to increase. And if the current is increased, what's actually happened is that the resistance has decreased. So what we've done here is actually the current has doubled, so the resistance must be halved. So in effect, adding an extra resistor in parallel halves the resistance. So think about that in terms of routes. So there's an extra route for the current to flow. And if you like, think about it in terms of road surfaces. So if you've got a road and there's a certain amount of charge flowing, is that really interesting? You want to get involved? Sorry, Casper is really interested about resistance. So if you want to think about it in terms of roads, and you've got a certain number of vehicles that are able to travel along the road. If you then build another route or add an extra lane onto the road, then what can actually happen, if you think about it, is that more cars, or the rate of flow of cars, will increase. So the analogy there is an extra resistance resistor in parallel is like building another road, another lane to a road, and the increase in number of cars flowing because of that extra road is analogous to the current flow. Okay, so current and resistance. Well, summarising all of that means that if the resistance of the current, if the resistance of a circuit rather increases, then the current is going to decrease, and that's vice versa as well. So if the resistance decreases, the current is going to increase, and what that means is that current and resistance are inversely proportional to each other. So if the resistance doubles, the current halves. If the resistance trebles, the current falls by a value of 3 or a third. Okay, so putting all of this together then, it gets us to a point where we can hopefully begin to understand something called Ohm's Law. And you need to know the definition of Ohm's Law, and it goes something like this. Is that potential difference, or voltage if you prefer, is directly proportional to the current provided that temperature remains constant. And that's the bit where the temperature remains constant is because we don't want to change the vibration of the ions. We want other things to affect the resistance. So as long as the temperature and the other physical factors don't change, that law is true. So what we can do is we can put this into some sort of mathematical format. So potential difference is proportional to current, or V is proportional to I. And what we can do here is get rid of that proportional sign, stick an equal sign and a constant. And here the constant is something called resistance. So here we have V being voltage, I current, and R resistance. V equals IR is the equation for Ohm's law. And resistance is measured in ohms after George Ohm. So let's have a look at an example then. So here we've got a question where 10 ohm resistor has 150 milliamps flowing through it, and we're going to calculate the potential difference across the resistor, or the voltage if you prefer, across the resistor. So the first thing to notice is that this question is a horrible thing again. The units aren't correct. Remember, we said that current must be in amps, and this question's provided current in milliamps. So first thing to do, convert that milliamps into amps, and we do that by dividing by 1000. So 150 milliamps is actually 0.15 amps. So that's the first thing to do. The second thing to do then is quote the equation. So once we've quoted the equation and we rearrange it, if necessary in this case we don't need to rearrange it, we can substitute in and we get our answer, and don't forget the units. So potential difference is measured in volts. Alright, let's have a look at another example then. So this time we've got a 3 kilo ohm resistor with a potential difference of 240 volts across it. And we're going to measure the current flowing through it this time. We'll calculate it. Again, check out the units. Not great in kilo ohms, so we need to convert kilo ohms into ohms. And we do that by multiplying it by 1000, so 3 kilo ohms is going to be 3000 ohms before we do any sort of calculation. Now we can write our equation down, but we need to rearrange it. So I is V over R. See you then. And we can substitute in, and we get an answer, and make sure that we're quoting the units as well. So I hope you found that useful in introducing the concept of resistance to you and linking it to what happens to current, and then getting to a point where we're talking about Ohm's law and looking at a couple of different questions that link to Ohm's law. Don't forget to subscribe to the channel. Hopefully it'll help you improve your understanding of physics, get those grades boosted.